we're down to chapter 5 here. It's the last chapter. And this is mitigation and prevention of DNS service disruption. So you must keep your DNS servers up. If they go down, people cannot access your websites. And if your recursive servers go down, your employees can't get to the internet. So it's an essential part of the internet. You have to keep it up. And there's a lot of things that can bring it down. One thing that can bring it down is just denial of service. When people deliberately target your DNS infrastructure, this happens a lot. Happened to Dyn DNS earlier this year. A lot of attackers that want to hurt companies will target their DNS as the weak spot. So your authoritative servers have to take queries from everyone on the internet. If you deny anyone access to your authoritative servers, they cannot get to any of your servers, and that sort of contradicts the whole point of having web servers and things on the internet. So you have to do something to handle the DOS attacks that can come in, since you're letting the whole world use it. So a network distributed system is one system where you put a variety of servers in different networks, like one in Comcast and one in Verizon and here and there, to try so that they can't all go down at once is the idea. That's what you're trying to achieve. Those would be different autonomous systems. You could also do it on a small scale at your own company, where you have different subnets, but in a larger scale you want to be different hosting providers and different networks. And you also have geographically dispersed systems where you put the servers in different countries, which is another way to just spread it out. And these were each effective against various kinds of attacks. You can get denial of service protection. There are a bunch of services you can pay to protect you from denial of service attacks, and they offer free levels of service too. What most of the people do is get content distribution networks. Content distribution networks hold whatever you want and serve it up for you. Akamai is the largest and the most expensive and the one standard everybody uses. And they will deliver your DNS records too. They'll also deliver your web page, your video, whatever you want. They'll deliver it from their servers so that their network takes the attacks and not yours. All right, you can get caching acceleration service. This is one way to do it, where you have a CNAME record on your servers and it just forwards you to the other server. The problem here is you still need your authoritative servers to stay up to provide the CNAME record. Direct delegation is more robust against attack, but now you have to trust the other people, because if you delegate your primary DNS server to be at the content distribution network, and the content distribution network goes down, your whole website is down. Here, every resolution has to go through your servers, but you don't really have to handle all the load. You have to give one small record instead of perhaps the large number of queries that would happen down here. There, your content provider handles all the load, but if they go down, you're dead in the water. So it's just your choice. Here's caching acceleration. Ask my server, and my server, instead of answering the question, will tell you, go ask this guy who has a lot of power and everything. Yeah.
Is that an Intel platform hardware, or is that a CERT?
Well, it could be anything. This is just the DNS server.
99 is just arbitrary?
Oh yeah, that's just arbitrary. Yeah, just an arbitrary name, nothing special. Yeah, and then you have a project where you set up your domain with Cloudflare, and when you do set up your domain with Cloudflare, you specify their DNS servers. So now everybody that goes to your website first goes to Cloudflare to find out where the IP address of the website is, and then they're actually given an IP address in Cloudflare's network where they can see a copy of your website, and none of that traffic goes directly to your servers at all, which saves you a lot of money and makes you very resistant to DDoS, but it does mean that if Cloudflare goes down or makes a mistake, you're toast. Of course, that's pretty much true of the other system as well, but anyway, here it's pretty harsh. So Anycast is the system, which is very complicated, and a lot of networks don't supply it, but this is what the big ones do, like the Redoop DNS and Cloudflare. They use Anycast, which means they have many servers at different geographical locations with the same IP address. So people that are trying to reach them, the Border Gateway Protocol will find the server nearest to them that is actually up. And if you try to attack any one of those servers, your attack will be smeared out around the world among all those machines. You can't attack any one of them because they all have the same address. So it's all or nothing. Unless you have enough power to take them all down, customers are not going to lose service. The worst thing that can happen is customers might not be able to reach the closest one, and they'd have to go to the next one and the next one, but they would still get service. So here's name server delegation. This is what I use on I use Cloudflare because it's got a free option, and I know the guys, they're cool. So if you go to dig my website, you will get answers telling you that the name servers are Cloudflare name servers. And if you ask for A addresses for my web page, you will get Cloudflare addresses. You'll never see my actual IP address. And under normal circumstances, nobody ever connects directly to my server. Just Cloudflare refreshes their copy now and then, and they serve up a copy. And that's the way it normally works. All right, there's other things you can do. If you just want to handle a lot of traffic, you could provide copies of your DNS servers for ISPs. Like you could give Comcast their own authoritative server for your domain inside the Comcast network, so they don't have to go outside the domain to resolve you. This is kind of like what Microsoft does with their business partners with a federated identity management. If you have a business partner, like Microsoft has their own internal servers that their employees have to use, and then they have payroll that's processed by ADP in Texas. And so Microsoft employees have to log into ADP servers to get their W-2 forms. And Microsoft got fed up with that, so they put a federated identity management server inside ADP, so the Microsoft Active Directory login is accepted inside ADP as identifying you, and customers do not have to log in again to go to ADP and get their stuff. And in the same sense, you could put an SOA inside some ISP, and now all the Comcast customers will go to that server and not to yours. So you don't have to beef this one up to take all the traffic. You just let them have their own to handle their large amount of traffic. That's one option here.
So what is it? What's the goal for them even using them ADP in the first place?
It's a good question, but I know they're the standard. That's why Ross Perot is so rich. He made ADP. I think it turns out to be the record keeping and taxation, where they do it and it ends up costing you less than doing it with your own people.
Yeah, we actually have the same thing. It's like your payroll, HR.
Yeah, their service is somehow extremely attractive. Almost everybody prints their payroll at ADP. And I think it's because it's much cheaper for them to keep up the tax law, and they give you everything in the right format for you to figure out your taxes. Because payroll taxes, I think, are a big burden for companies with a lot of employees. So every company I know with more than a few hundred employees, ADP prints their checks. And therefore, they all have this issue that all their employees have to have an ADP login to get their W-2. Now, that federated identity management didn't work out so well for Microsoft, by the way, because they had layoffs. So in like October, they laid off some people, so they no longer had Microsoft Active Directory logins. So when it was time to pay their taxes, they couldn't log in and get their taxes. So there turns out to be a fly in the ointment. Anyway, all right, so Ultra DNS works this way. They will place authoritative servers all over the place to private companies. They will rent you servers inside here to be the authoritative server, so these customers don't have to go back to your official public DNS server. And that's just another service you can pay for. You're renting somebody else's server time to do any of these things. Just like Cloudflare, you're renting some time on their servers. All right. And they call this thing Ultra DNS Shield, where they create copies of your DNS records all over the place inside ISPs and elsewhere, and that means customers all over the place can go to the Ultra DNS servers to get resolved resolution. All right, there are many DNS software products. In this class, in Windows, you set up Windows DNS Server, and you probably noticed how terrible it is. Almost nobody uses it, except inside companies to go with Active Directory, because you kind of have to. But as far as serving like authoritative records to external people, it is very inefficient and people don't use it. Bind is the standard that started it all. Bind is comparatively slow, and it had an awful lot of bugs and security problems down through the years. So there was another one, DJB DNS was an alternative intended to be more secure, but it seems to have been abandoned. But there are many other DNS software packages out there. It really is not a very complicated protocol. You just take in these requests, serving out these records. It's sort of like an online distributed database, much simpler than, say, MySQL. And there are just a lot of different software packages that do it. So that's the availability of DNS. Now we can try testing other kinds of security, like DNSSEC. Now the point of DNSSEC, for better or worse, is to provide integrity and authenticity. So when you get a DNS resolution from, say, City College telling you that a server is at a certain IP address, you know that it is the right IP address and not a lie put out by a hacker. Because without DNSSEC, anybody on the network can just put out false DNS replies, and your machine will just believe it and go there. You can just poison DNS, and no machine knows any better, because the legitimate DNS record does not come with any proof. There's no way to tell it from a fake DNS record. So that's the game here. So you do it by signing resource records. The resource record is the record that has an answer that you care about in it, like an A number, IP address, and the resource record signature is the mathematical signature which proves that that is the right record from the right company. So, just like HTTPS, SSL, you now have to have a chain of trust. There's no trust-free system. There has to be somebody you trust to tell the truth. Now in DNS, you trust anybody that answers the question, and that's not considered very smart. So now you're going to try and somehow to trust people. So what you do, you have a resource record, and it has a signature. People can verify the signature by going to the public key. Now the public key came from the same server. Now so far, you're getting nowhere because the attacker could just give you a false record, a false key, and a false signature, and it would match. So the reason why you can trust this is you're going to have to go up, walk up the chain. This is the same thing you have to do with HTTPS. So you're going to have to ask in the parent zone, is this really the right key? Or did somebody lie about the key? So the parent zone has to have a record that verifies the key, and then the parent of that has to have a record to verify that, and you have to walk up the chain right to the root. That's how it works. And so here's the game. If you go to ietf.org, they give you an answer, they give you a RR-SIG, and they give you a key. And you wonder if the key is right, and you check the key signature at org. And they say, yeah, that's really the key. And then you wonder if these guys are lying, so they give you a key, and you check that key at the root. And if the root says it, you just believe it because you have to trust somebody. Because there's no higher authority than the root, so the root's key is self-signed, and there is no verification record higher because there is nothing higher. And therefore, the root of DNS is super important. And as mentioned before, the root of DNS its integrity is maintained by a cryptographic key that is broken into, I think, 8 pieces, and 8 people carry this key. They own it as personal property, and they have a key signing ceremony every year where I think at least 6 of those 8 people must come together, and Dan Kaminsky is one of those people. So instead of being just big corporations that make a lot of money that we trust, there are just celebrities in the community that people trust, that they are entrusted with holding part of the key. And they have a key signing, every year they have a key signing event where they meet, put the key together, and verify that nobody's been messing with the root. And that's why we trust the root. So here's how it looks in some more detail. I got it from this web page. So you go to example.net and you want the A record. Then you wonder if it's right, so you get the RR-SIG record that goes with it and the DNS key that goes with it. And you check that this signature can be verified using that key. And you wonder if this key is any good, so you look at the DS record above it, which is a summary of that DNS key record, something like a hash. And if this matches, then this server is vouched for by that server. And now you just do it again. You have a resource record signature and a DNS key here, and you look at the DNS record in the root to see if this key has been altered. And if it passes that test, then you're done. Then you believe, and you know this is okay because it's signed by a key up here. So you can verify, as long as nobody has managed to hack the root, that nobody is lying to you about the resolution of example.net. That's the game. All right. Now, this was all completely theoretical until 2010 when the root was finally signed. Before that, people developed the protocol and developed the software and tested it, but nothing could ever do any good until the root was signed. Now the root is signed since 2010. So you can see all these things. So if I go, I can do it going down. Let me bring up a terminal. All right. And make it big. All right. And let me shove this to the side. Okay. So I can dig dot. And that will tell me the start of authority for the root servers. Now I might want to do the RR-SIG for the dot, and I'll see a bunch of cryptographic signatures that came from the root of DNS. So those long cryptographic signatures contain information to verify the records it's going to tell me. All right. I can also look for DNS key. And there'll be a bunch of keys up there. Again, long, so you have to do some public key encryption on these to verify them. Now, if I dig for DS records at org, I will see that it does have some DS records. And if I dig for DNS key at org, It's got keys, and it's got RR-SIGs also. All right. And if I go down to ietf.org, ietf.org has got RR-SIG records, and it's got DNS key records. I don't think it's going to have any DS records unless it's signing something even lower in the system. It does have a couple. I'm not quite sure what those sign, but anyway, these are the records you see, and now you do some math on all those things to verify them. And there are various tools you can use to do the math in principle, although I couldn't find any that works this time. So I just saved those in case it didn't work. So this is rolling out very slowly, like IPv6 did. If you're at a company and you're the IT guy, you go to your boss and say, we need to have DNS-SIG, DNS-SEC. Your boss is going to say, why? What more product would we sell? How many customers are leaving us and going to some other company that has DNS-SEC? And the answer is 0. There is no browser anywhere that verifies any of this. No end users are using it at all. So it's growing very slowly because it's just sort of a stunt right now. The same thing was true of IPv6 for a long time, until about 2-3 years ago. So anyway, you see it is growing, but it's nowhere near the point where end users are actually getting any good at it. But what's happening is the servers that are updating their caches are actually enforcing it at a higher level, and they're getting some benefit from it. Anyway, there are browser extensions you can put on that should tell you if things are signed, but the ones I tried are all buggy and not working. I found one for Firefox, I found one for Chrome, and they both just told me nothing. Oh, the Firefox one was kind of funny. That would tell me about the last domain I went to, not the current domain. And the other one just always told me it didn't know the answer, so I don't know. In principle, you can put on some kind of extension and verify the DNS of your records, but it's all like beta versions, and I think you saw this in a project when you try to do some of these experimental DNS protocols. Here's another one that's kind of cute. A lot of people say, since we have a DNS system and it has a root of trust, why don't we just use it instead of HTTPS? We could put certificates on the DNS chain, and then we'd have another way to distribute public keys. So why do we need to bother with certificate authorities and all that? And that's what DANE is, DNS-based authentication of named entities. DANE is the protocol that distributes digital certificates over DNS-SEC. And in principle, it could be just as good as the other HTTPS. It's just you have a different idea of who to trust at the top. It's not caught on, it's not very popular, but you can put on experimental software and play with this if you like. All right, so here's the issues. The protocol is still changing. I remember this all happened with IPv6 too. It only secures record to resolver, not the traffic from resolver to client. Like I say, your client doesn't get any direct benefit from this, and it does not protect your privacy. It doesn't encrypt anything at any level. It's just integrity and authentication. So everybody can just still scan the traffic on your network and see everything you're doing. They can see the domain names you're going to, which is pretty rude. Anyway, this is why if you want to, it's why it's a good idea at companies to not let people use public DNS servers like 8.8.8, because if you force them to use your company's DNS server, then at least all those unencrypted queries are local. And your DNS server sends the traffic out, and you have a chance to filter it and make sure that they're not doing what they shouldn't be doing and all that jazz. Whereas if you let them go straight to the public, then they're spraying all their DNS queries all over the internet in a way that you may not want them to. You'd have more control if you forced them to use your own resolver. It also makes it easier to monitor the DNS because you know where all the traffic is going. And you can see all the domain names that are being resolved, and that's commonly what people do at like high schools to block sites they don't want people going to, like Facebook and porn sites and stuff. They just block the DNS resolution. All right, now one of the thorny issues of DNS is authenticated denial of existence. If there is no server named fred.ccsf.edu, but how do you find that out? You could do a dig for fred.ccsf.edu, and the authoritative server will not answer because there is no Fred. And you don't know if it didn't answer because there is no Fred, or if it's down, or the query got garbled or something. Not answering is not enough to prove that there is no Fred. So you would like to be able to ask it, is there Fred, yes or no, and get a no that you could trust. Now that's fine. There have been many versions trying to make this record, and they all have had serious problems. The next record, the NSEC record, now the NSEC 3 record, all incompatible with each other, all using different systems to try to answer this question. And one of the bizarre things here is people regard zone transfers as a security flaw. Now, if you ask me, I don't understand why, but it's largely because of Microsoft. The point is DNS servers do contain records that people don't want to be public. And what they ought to do is have a local DNS server to have all those automatically generated Microsoft records, and they ought to have a public server that only has public records. But the fact remains that people do have server names in DNS that they don't want people to find. So they don't want to make it possible to use this system to find all the records on your server. And trying to do that is what made it pretty hard. So TSIG maintains the integrity. This cryptographically signs messages with a transaction signature with a key shared by the end nodes. So now you have to generate a secret key and you have to share it with all the servers. So that's a pretty unpleasant key handling issue. All right, and originally it was written to only use MD5, which is a really bad idea. MD5 was never approved by the government for any purpose at all because MD5 is just not a very good hash function. It's not long enough. It's only 128 bits. So anyway, they eventually updated it to SHA-1 and SHA-2, which makes it better. So SIG0 was an alternative method using public key cryptography. And then came T-keys. This established a shared secret using Diffie-Hellman key exchange. So you share key information over the network without sending keys directly. So it's difficult or essentially impossible to steal the keys. But this is, of course, vulnerable to man-in-the-middle attacks. Diffie-Hellman is totally vulnerable to man-in-the-middle. There is no trusted third party like a certificate authority, so a man-in-the-middle can just intercept the records and lie to both ends and end up having all the keys to read and alter the traffic. All right. These are various options here, and all these things attempt to solve the problem of verified non-existence of a server. Anyway, another issue is software variety. Bind in particular has had many disastrous vulnerabilities. Remote code execution vulnerabilities, denial of service vulnerabilities, and so on. So if all the servers were running Bind, it would be very easy to write sort of a virus to wipe them all out. So people often use a variety of different ones, and the K and H root servers use this thing called NSD from KL NetLabs instead of Bind, so that hopefully if you use multiple software products, they will not all have a similar problem at the same time. All right, so you got a master-slave setup. You've got a primary master, which contains the master copy of the zone. These do zone transfers to update slaves, and they do zone transfers to update other slaves, so all these guys just have copies of the data. This looks pretty good, but it can fail in entertaining ways. This happened to City College about 2 years ago. Students complained to me, the website is down. I'd look at it, and it's up now, it must be all right. Then they come back next week, it's down again. I couldn't take my quizzes, and only half of them. And I found out, one of my student at Cloudflare figured it out. Nobody at campus could figure it out. I couldn't figure it out. What happened was they changed the primary master so it went backwards in time. There's a version number on all these updates. So this was like at version 100, and for some reason this went back to version 99 because there was like a crash and it restored from backup or something. So now this slave, like this slave here, had a version 100, and the primary one had version 99. So this one would get told version 99, and then would get an update from here with version 100, and update to 100, and then would get another update going back down to 99, and it would just flap back and forth. So the servers would give you the wrong address for a while, and then the right address for a while, and then the wrong address for a while, and this was just going on forever. So it would drive you nuts. Some students couldn't get to the site, other people are getting there. I've seen this happen to my students in other classes where they set up DNS resolutions and change them. You can get it so confused that it never settles down. There are just a bunch of servers sending false updates, undoing each other's work. It's a surprisingly inefficient and messed up system. Usually it works just fine, but when it goes wrong, it goes very wrong. So here's how you make a slave server. You just tell it, type slave, and then you tell it where the master is, so it will just get all its data from the master. And you don't need to configure any more data here. It will just constantly follow the master by copying whatever data it gets. All right, running a lot of slave servers is of course good for fault tolerance. If you get if one of the slaves goes down, it doesn't matter. You got other slaves, but they all need to be listed as authoritative servers. Now, in legacy systems, DNS was limited to 512 bytes. So you can't have too many name servers, or your message listing your name servers will not fit in 512 bytes. The number of records you can answer for an A record is about 13, and if you start having signatures, it's much less, and if you start having IPv6, it's much less because the answers are bigger. So it's a problem. Now you can have multiple name servers, and if you do have multiple name servers, people that can't resolve at one will go to the next, but that's slow. They'll wait for a timeout at the first one before they go to the next, so it will still irritate your customers, even if it doesn't mean that they totally can't reach the website. It will be very slow in responding. So CCSF used this system in 2015. We had 4 name servers, and this is for failover and load balancing, but it means if this one goes down, the people that happen to have it at the top are going to be waiting like 10 or 15 seconds to open the website, which is not ideal. On campus, we now have just one, but I happen to know our on-campus system is different than our off-campus system. But on campus now, we have just this one, VMNS01, which is new. It used to be something called Rudra. So I think they've been changing our DNS structure, and I'm not quite sure what to make of the new one yet. I do know it is spectacularly inefficient. I've been trying to use our on-campus servers. In fact, let me try this now. If I do cat ets resolve, okay, when you're on campus, you get these 2 name servers, 172.16.2, 252. And I was getting bad performance out of them yesterday, and I just tried this. If I do dig at one of these for anything, like say yahoo.com, okay, I got an answer. Oh, there we are. That was slow. 7, 8, 9. It's much better today. When I did it a couple days ago, like 2 out of 10 would time out completely, and a bunch of them would make me wait for like 10 or 15 seconds. So there was some kind of problem. I wonder if 253 is working. 2, 3, 4, 5. Oh, okay. It's working pretty well today. Laura Chappelle, who is the expert at using Wireshark and improving networks, says when people complain that the network is miserable and I can't get my work done, it's almost always DNS. And I certainly found the same thing. It is very common that the DNS resolvers get slow or unavailable, and you're waiting, and it's DNS that's not responding typically. That's why in practice, I very often do move to those public servers like 8.8.8.8 because they're always up and they're fast. And very often, the official DNS servers are not responding well enough to satisfy me. So if you have multiple servers and you don't want to have this slow cluster caused by issuing many NS records, the more professional way to do it is to buy a load balancer. So you get something like F5, I think is one brand that does it. Other people make it. Buy this thing, which now will let you have various servers. Customers come in with one IP address and they think they're talking to one server, and this device sends some traffic here and some traffic here and to all your things. They don't know they're using many servers. So this is fine. And it appears to be an external server, a single server to the outside, but inside your load is being shared by many servers. Now, one simple system is automatic failover, where you use one and you have a heartbeat to tell you this one is alive. And when this one crashes, the heartbeat stops, and then you use the other one. Now, what happened to City College several times is one server went down, but the heartbeat kept going. Because servers are not all or nothing. It doesn't go down and everything crashes, so it didn't go to the other one. That's one of the many problems with automatic failover. The automatic failover might not fail over, and then you haven't gotten anything. Anyway, so if you want to protect your DNS servers, you run them on hardened systems, remove unnecessary code, unnecessary other services. Firewall limit them, so the only thing open is port 53, TCP, and probably UDP. If you have a management interface, you should not expose it to the internet, but only expose it to trusted IP addresses so people can't attack that. That happened about 4 years ago. Some DOS attackers started figuring out that what's really cool, rather than trying to flood a network or a server, is to find the management interface for the switch and flood that, because that can't take much traffic. And then nobody can adjust the switch. So those shouldn't be public. IDS and IPS will block attacks, and you can have access control lists. Just be aware that if you have older equipment, it's going to assume that all DNS packets are 512 bytes or less. And that may get you in trouble. If you are under attack, one technique that is used, and Cloudflare will do this for you automatically, so you don't have to worry about it, but if you're running your own system, you have to set up your own scrubbers. Scrubbers are special servers just to remove the bad packets. So when you're under attack, you have to somehow tell the bad packets from the good packets. The examples I heard at conferences were the Al-Qassam Cyber Army. About 5 years ago, a bunch of Islamic people got angry about a video insulting Muhammad on YouTube, and they decided to attack American banks to punish them for that. And they had something like 12 waves of attack. Like every 3 weeks would come another wave, and they announced them. They announced how long they were going to be. They had mathematically calculated how much insult had been done and how much punishment we deserved. And so the banks knew that attack was coming, and it would come, and they would have to do this. So the first time they attacked, the packets all contained just the capital letter A like 300 times. So it was very easy to identify those packets. So all you had to do was build a scrubber. This is what you do. Normally, your customers are coming in, and they come in from all over the internet, and they go to your site and they view your page on your server. But if you have a scrubber, you take all this data coming in from the outside and you send it to a scrubber site, like an Amazon virtual machine, which is a very fast proxy, and all it does is look for certain bad things and remove them, and let the rest go through. So this cloud service that can take a lot of traffic, and that's what you do with the Al-Qassam cyber army is attacking you, so you throw away all the packets with more than 100 A's in a row here, and let all the rest through. Now you're back online. Yeah?
Those attacks, weren't they just getting heavier, worse and worse?
They were getting smarter every time, yes. The original ones were extremely simple, and every generation they got better, so they were improving their game.
So the scrubbers work and...
Well, every time people had to reinvent, had to fix the scrubber. Every time an attack comes, you'd have to start taking the packets, then analyze them, try to find some way to tell the good from the bad, and program your scrubbers. And then the banks had communication lines to each other. So they would say, okay, we figured out what to do, use these rules. That's how it generally works. You form like a club. And so when they gave these talks, they wouldn't let you record them and stuff because they had to keep it kind of secret how they figured out how to do it, because they were trying to prevent it from leaking back to the Al-Qassam cyber army, who would then know what they did. And that was an unusually public example of what goes on all the time. There's a ton of attackers, and people figure out who the attackers are, and they customize defenses, but normally it never becomes publicly discussed. All right, so you can monitor your traffic to see if it's working. You should be sending some traffic just to see if your servers are up. Smoke ping is one tool used from this. Another one people use is Nagios in the world of Linux, and there's a lot of commercial products. Here's a simple test. If your server goes down and your boss calls you and says, why is my server down? You're going to need a new job pretty soon. That should never happen. You should have automatic sensors so you know your server is down, and then you call your boss and say, oh, there's a problem with the server and I'm working on it, before the customer calls him, because you're not an idiot, and you run automatic tests that test your server every few seconds, and when it's not there, it sends you an IM or rings your phone, or otherwise, you should know. You should be the first one to know when your servers are down. If you find out from someone else, you won't be around much longer. Anyway, you got to back up your servers. Any system will do full backups, incremental backups. You could back up the whole OS, but normally you just back up the configuration files because the OS should be pretty simple. Your cloud DNS servers have to be backed up too, and you have to test your backups. One common mistake at companies is they have a backup system and they don't test it, and the people do it wrong because you don't really need the backups in normal daily activities, and when you go to reach them, they're not really there. So you do have to have a regular test of your backups to make sure it's really working. All right, so like I say, if a DNS server is down, it slows down responses because people try to use the dead server and then they wait for a timeout before they try another one. So if you do have a server that's failed, you should stop advertising it as a name server for a while until you get it back up so fewer customers go through this frustration. All right, I got a few Kahoots, and it looks like we're right on time. 5 questions. All right. What architecture puts authoritative servers in different ASs? Okay, that's network distributed. They're in different networks. Okay. All right, what DNS delegation system does Cloudflare use? Okay, they use direct delegation. You have to trust them completely. They are your DNS server. If Cloudflare goes down, you're down. And they have had a couple of brief outages, Nobody's perfect. Amazon's gone down for 4 days, Cloudflare's gone down for like, I think 15 minutes one time and a half hour another time, I think. That's the risk you take. All right. What system encrypts DNS requests? That's good. None of them. Not DNSSEC. DNSSEC does not encrypt anything. It just puts an authentication signature on it. This is actually a huge problem. Encrypting DNS is probably the main thing the end user would really like to protect their privacy, and none of these do any of that. Now there's a project where you set up, I think, DNS crypt, but as you may have noticed, all the software to do that is like just a beta. It's not ready for prime time. I'm surprised how little interest there's been in this. Everything you do is visible to everybody around you, and that's rude and unnecessary. Unless you run through a VPN. If you run through a VPN, then all your stuff gets another layer of encryption on top, and that in particular would encrypt your DNS along with everything else, if it's set up correctly. But I should mention, tests show that 80% of actual VPNs forget to run the DNS through the VPN. So they don't actually protect your privacy unless they're set up correctly, and usually they are not set up correctly. Anyway. So which record will provide authenticated denial of existence? The NSEC3 record does that. All right, and which system removes the need for CAs? Okay, that's DANE, which distributes certificates through DNSSEC. All right, so I guess that's it. I'm gonna put this video up. I'm going to the lab to help anybody who wants help on projects.